Okay, so last class we kind of talked about just how to calculate probabilities, look at some of the basic concepts with it. Now we want to get a little bit more into details with them. So the one thing, and you can kind of read, some of the description, but one thing I wanted to point out is the smallest probability that you can have is 0, because we're saying basically the chance of this event happening is 0, which means, it cannot happen. And remember, we had talked about this as being an impossible event. So anytime you have an event that would have a probability of 0, we're basically saying that event cannot happen, which means it's an impossible event. And that's kind of what we're talking about here in rule 1. The maximum probability that you can have is 1, because that's 100%, right? So we're saying it is a certain that this event will happen, right? That means we're saying 100% there's a chance this event will happen. So a lot of times when we talk about the sample space, we can say the sample space will have a probability of 1, because that lists all the outcomes, right? Your sample space, we're saying everything that can happen will happen within the sample space. So if all of those events are happening, we can say, yes, your probability is 1. For anything in between, depending on the event you are looking at, so the idea is your probability has to stay between 0 and 1. So you cannot have a probability which is less than 0, which means you cannot have a negative number for a probability, and you cannot have a number larger than 1, because even though we may be used to saying, I'm going to give this homework or whatever 200% of my effort, you really don't have such a thing as 200%, when we're talking about chances. So the maximum you can have is 100% probability, or 1. So that's why your probability values have to stay between 0 and 1. And these 3 rules are, definitely kind of like the foundation, when we talk about probability rules. So those would be some of the things to kind of keep in mind. They're giving you some examples over here just to, kind of help you play with these 0, 1, and in between kind of probabilities. Now, if you also remember in chapter 2, we had talked about mutually exclusive events. And this is where, if you don't have anything overlapping between any 2 events, we say that, they're mutually exclusive because they both have nothing in common. And you can kind of see they're talking about 2 events that cannot occur at the same time. So both the events cannot occur at the same time. We're saying they're mutually exclusive. And in set notation, we're basically saying if you tried to do an intersection between the 2 sets, it would be an empty set. So they're showing you this example over here, which is kind of neat, because they're using Venn diagrams. So again, we're using set theory to help us out with these probabilities. And you can see where all 3 of these events meet, that's an empty space, because these are mutually exclusive events, right? So you can see there's no number over here. And in this case, they are defining event E to be even number that comes up when you roll a die. Event F is defined as a number which would be greater than 3. And event G is defined as an odd number that comes up. So if you look at all 3 of these events together, then yeah, you can see the center is going to be an empty set. And they're showing you, between 2 overlapping circles, you might have something in common, but all 3 of the circles don't have anything in common. So as far as each of the 3 circles are concerned together, that's what we're saying they are mutually exclusive. For that matter, you can see set E and set G are also mutually exclusive, because again, set E is defined as even numbers, set G is defined as odd numbers. So obviously this space is also blank because you will have no overlap between odd and even numbers. So you can see we're also saying sets E and G are mutually exclusive. So that's kind of what they are, just giving you a little highlight of how you can use this idea of mutually exclusive events. And then, again, based on that, we can come up with our probabilities also. Here's just another example of using dice. to help us calculate probabilities. And in this one, they're talking about, rolling a pair of dice. And in this case, again, you can kind of see they walk you through different examples, what chances are that this event will occur. So one thing that you will need is, what does the sample space look like when you are rolling 2 dice? So again, this is a great table over here to show you what the sample space would look like. And you can kind of see the different numbers that will show up, when we roll these 2 dice together. So there's going to be a total of, what is this, 36? 36 outcomes in this experiment over here. And then based on that, we will be able to come up with different probabilities. So just to show you kind of some of these examples. So what is the probability that when we roll 2 dice, the total will come out to be 7. So when you add the 2 values, and you can see they are actually showing you, if you're looking for a total of 7, that's going to be these outcomes over here. So if you follow along that line diagonally, you will see all of those combinations add up to 7. 6 plus 1, 5 plus 2, 4 plus 3, and then we're just changing the order, 3 and 4, 2 and 5, 1 and 6. So out of a total of 36 events, we've got 1, 2, 3, 4, 5, 6, which are going to add up to 7. So that's 6 out of 36 outcomes. And, of course, when you reduce that, it becomes 1/6. And you can kind of see they're talking about that right over here in your example. So coming up with the sample space, and we had looked at some examples last class with 3.2, come up with your sample space, and then you can calculate the probabilities. Like the second one is saying that the sum is going to be greater than 9, which means the total would add up to 10, 11, or 12. So that's going to be these outcomes over here. And again, you can see that's a total of 6 outcomes from 36, which will of course also give us a probability of 1/6. And you can see that over here in part B. So that's kind of how, they're showing you just different ways that you can use set theory combined with Venn diagrams, and how that can lead you into coming up with your probabilities. So again, I would say take just a little time, if you haven't already looked through the handout, to just get familiar with some of these examples and properties. So we have a couple more probability rules that I wanted to talk about. And again, guys, you should recognize these coming from our set theory. So in set theory, if you remember, we had talked about these cardinal number rules over here that you can see right at the top. So if you take the cardinal number for the union, you can calculate by adding each one of the individual sets A and B, and then subtracting any overlap that might be happening between those. So you subtract the cardinal number for the intersection. That's the same rule which is translating over here as a rule for your probability. So instead of a cardinal number, now we're saying use the same principle to calculate your probability rule. So again, for A union B, you take the probability of A plus probability of B, and then subtract the probability of A and B happening together, which gives you the probability for A or B. For your complement rule, basically with the complement, you take the size of your sample set, subtract the cardinal number for A, and that gives you the cardinal number for, A complement, which is everything that's not in set A, right? So that's the same rule that's translating over here with probabilities. So remember, the probability for a sample set is always 1. And we saw that in our rule 2, I think. Yeah, so you can see, oops, with rule 2, we said probability of a sample space is going to be 1. So that's the rule we are using over here. And we are saying, come on, buddy. So again, instead of saying probability of the sample set, since we know the probability of sample set is 1, that's why you have the 1 over here. From that, subtract the probability of event A, and you get the probability of the complement of event A. So those rules are listed right over here. Between rule 4 and 5, guys, you should notice that they kind of start out the same way. So you're looking for the probability of E or F, which is coming from, this rule. The only difference with rule 5 is if your events are mutually exclusive, then that means for mutually exclusive sets, this probability here is going to be 0. And that's the reason why in rule 5, they're just saying add probability of E with probability of F, but then we don't have to subtract that E and F because we know that probability is going to be 0. So remember, this only happens when your two sets are mutually exclusive. So I would say, remember rule 4, because rule 5, the only difference is this part, ends up becoming 0. So if you just remember rule 4, it serves the purpose for both rule 4 and 5, but obviously they're just showing you what happens if you have mutually exclusive sets where your intersection is going to be 0. So that's it. And then of course your complement rule 6 over here. So again, you've got a couple of different examples to kind of walk you through that process of calculating your different probabilities based on the rule. And then the last part over here, again, is kind of tying us back with set theory and probabilities and showing us how we can, with probabilities, also use a Venn diagram to come up with answers. So that's kind of the general idea behind 3.3. So let's go ahead, take a look at some examples over here so we can practice these rules ourselves. And how about we actually start right here with problem number 2. So again, our instructions for these problems are determine whether sets E or events E and F are mutually exclusive. And they're saying write the sentence justifying your answer. So let's start with number 2 over here. So E is described as the event it is raining, and F is described as it is sunny. So the idea is we're trying to think about if they are mutually exclusive or not. So basically the question is, can these happen at the same time or not? So what do you think? Are they mutually exclusive or not, and why?
I think they're not mutually exclusive because it has to be cloudy for it to rain. Well, at least some clouds.
Okay, so you're saying if it is sunny, then it cannot rain? Okay. What about anybody else? What do you guys think? Are you in agreement with Logan, or do you have a different point of view? Because to me, it sounds like what Logan is saying, that if it is sunny, then it cannot rain, which means the events would have to be mutually exclusive with that reasoning, right? Because our idea is, can they happen at the same time? And if they can happen at the same time, they are not mutually exclusive. So think about it once more. Can it be sunny and still rain? I mean, we live in Colorado. Our weather changes, what, hour to hour? I mean, I was freezing my butt yesterday. I was ready to turn on the heater, and today it feels pretty okay. So I'm kind of disappointed. This is such a simple example, and I've only got one answer. Where would rainbows come from, people, if it wasn't sunny and it didn't rain? At the same time, they are not mutually exclusive events because it can be sunny. I mean, it doesn't have to be, bright and cloudless. I mean, definitely you need some clouds, but remember, you can still have some clouds, but not, completely cloudy sky, and you can still get some rain. So this is actually not mutually exclusive because both can happen at the same time. So that's kind of our reasoning for this guy. And then you can see they're giving us a whole bunch of different examples, kind of like if you look at 4, again, they're just using basic, simple examples. Event E is having naturally blonde hair. Event F is having naturally black hair. So, and they're emphasizing naturally, so it's not, colored. And so the idea is if a person has naturally blonde hair, at the same time, can they also have naturally black hair? Not really. I mean, as you age, your color can change, and you've seen that with, especially with kids, you see they will be born with, certain hair color, and then as they get older, it, darkens or lightens or whatever. But at the same time, so in this given moment in time, if you have naturally blonde hair, then, obviously you will not have naturally black hair. So in this case, we would say yes, they are mutually exclusive, because they cannot happen at the same time. So you will definitely see some examples like this in your homework, just to, get us comfortable with the idea of what events are mutually exclusive or not. All right, now let's look at, how about number 16 down here? So again, our instructions for number 16 are, they're saying a card is dealt from a complete deck of 52 playing cards. Again, that means no jokers in there. And they're saying using the appropriate probability rules, find the probability that the card is as stated. And again, they're telling us to keep ace as a high card. So, Jack, queen, king, and then an ace. All right, so number 16. There we go. And they want us to find the probability for, each of these events. So let's start out with part A. They want to know what's the probability that the card is dealt is going to be a card above a jack. So above a jack, so of course, what cards fall under that category?
King and queen.
And?
Ace.
Yeah, because remember, they also told us to think of ace as a high card. So the 3 cards we're talking about is queen, king, and ace. So, when we're talking about probability over here, we're basically trying to find the probability of card being above a jack. So if you think about it, that means you are looking at the card can be a queen or a king or an ace. And again, they're not emphasizing any suite, right? So it's just a jack. It can be any of the 4 suits that you have in your deck of cards. So, when they're talking about using the appropriate probability rule, you can basically think about, those rules we looked at. And let me see if I can bring that guy up. So kind of like rules 4, 5 over here, because this is where we look at, E or F as our event. So the first thing I want to ask you is, are these events mutually exclusive? Which means if you get a queen, at the same time, can you get a king? Or at the same time, can you get an ace? So are the events of queen, king, and ace mutually exclusive? So if you pick a card from your deck of cards, can it be a queen and a king at the same time?
No.
No, so that actually means these events are mutually exclusive. And since they are mutually exclusive, oh, wrong one. You actually just need to add each individual probability like we saw in rule 5. So we wouldn't have to worry about the intersection, because like I said, with mutually exclusive events, your intersection is 0. So our breakdown here is basically going to be adding the probability that the card can be a queen with the probability of a king, and with the probability of an ace. So what do you think this comes out to be? So take a minute, calculate your answer and get it ready, and we'll share it in chat like we normally do. So think about, how many cards in the deck of cards are queens, how many are kings, how many are aces, and then based on that, you can come up with your probability. And just as a general rule, if we're talking about how many cards are a queen, you're looking for the number of cards, which will be a queen divided by the number of cards in your sample set. And that will give you your probability. And, of course, this will be the same for king and ace over here. And then adding them together should give you the probability. And we will leave our answers as fractions over here, guys, not as decimals or percents. Okay, so get your answer ready in the chat. Okay, go ahead and send it in, guys. Alrighty, Brandon, Ethan, Nicholas, Hidali, Riley, Logan. All right, Cynthia. Okay, very nice. Yeah, and again, like we talked last time, whenever you are dealing with fractions, you definitely want to put them in lowest form. So in this case, again, just kind of looking at the general form, there are 4 suits. So each one of them has a queen. So that's going to be a total of 4 out of 52. So you can leave it as 4 out of 52 for all of them if you want, or you can reduce this down. And 52, I think, should be 13 when you divide it by 4, but let me verify that. So yeah, 4 goes into itself once, goes into 52 13 times. So each one of these probabilities is going to be either 4 out of 52 or 1 out of 13. And in this case, you can see, since our denominators are the same, we can just go ahead and add the numerator. So that adds up to a total of 3. So very nice, guys. And then for the rest of you who gave me the 16 out of 52, just make sure you are reducing your answer. But yeah, that's a good starting point. All righty, perfect. Now part B, same deck of cards, same rules, but now they are asking us what is the probability that we get a card which is going to be below a 3. Oops. So this should be probability of below a 3. So what cards are we talking about when we are looking at a probability for a card to be below 3? Yeah, Brandon, very nice. It will be just the 2, right? So what will this probability come out to be? Because again, they're not telling us a specific suit. So obviously it means all 4 suits. So same thing, out of 52 cards, 4 of them are going to be 2s. So again, it's going to come down to just 1 over 13. So yeah, very nice, Brandon. And actually I erased that, but let me go ahead and put that in here so we know how we are doing our calculations. Okay. So let's see, this is below a 3. Now they're asking us, what is the probability that we get a card which is above a jack and below a 3? So I want you guys to think about what you think that answer should come out to be. So don't send me the answer. I'll have everybody answer this one together. probability that a card is above a jack and below a 3. Okay, so I'm actually going to clear this so we can make room for parts C and D. So what card do you think falls under the category of above a jack and below a 3? That's what you're asking yourself. And once you figure out what that card is or isn't, you will then have to decide how to calculate the probability for it. So take another couple seconds and then let me see what answers you come up with. All right, guys, go ahead, send me your answers for above a jack and below a 3. All righty, I've got, let's see, 4 out of 13, 4 out of 13, 4 out of 13. Okay, everybody looks like has 4 out of 13. So we've got Logan, Adali, Roman, Nicholas, Brandon, Riley, Cynthia, Ethan. All right, so now I am curious, how did you come up with this probability?
Just adding the first two together.
Okay, that's what I thought. Yeah.
Yeah.
Okay. So what card is that then, guys? I mean, they are saying the card, a single card that you're going to draw from a deck has to satisfy both conditions of being above a jack and below a 3. So what cards are those?
That would only be the ace card then, right?
Well, not if we are thinking of ace as being a high card, right? Because they're telling us to think of ace as a high card, so which means we cannot technically use it, at the lower end than with the 2s and the 3s. So this is where that tricky part comes in. So what's happening over here is, because if we talk about a card being above a jack, remember those cards are queen, king, and they are specifically asking us to use the ace as a high card. And then below a 3 is 2, because that's what we did in parts A and B, right? So that actually means, look at those cards. There is nothing in common, because with queen, king, and ace and 2, there's no overlap happening. So actually, this is a probability of 0, because these are mutually exclusive events. So it does get a little bit tricky, because like you guys did, you added the answers from part A and part B. But when you really start thinking about, okay, what card will actually fall under, both of these categories, you realize there's actually nothing. And that's why your probability comes out to be 0. Now they're doing the same thing in part D, but now they're saying either it's above a jack or it's below a 3. So above a jack, again, obviously is those same 3 cards. Below a 3 is 2, but now they are saying or. So again, take a minute, and it's okay if, the answer is incorrect, because this is what we are trying to do, is make sure we understand the difference between the terminologies. So they're basically saying if the card is above a jack, and how do I want to write this? We do know these two events are mutually exclusive, because we just saw that in part C. So I think you could almost write it as rule 5 that we saw before. You take the probability of above a jack and add that with the probability of below a 3, which is what you guys actually did for part C, and that was the answer for part D. So our probability for above a jack, what did we have? 3 out of 13. For probability of being below a 3 was 1 out of 13. So this is where, again, having a common denominator, you just add the numerators, and this gives you 4 plus 13. So big difference in your answer when you have the word and or you have the word or. Do you guys see the difference between part C and D? Does anybody have a question on that? Okay, so yeah, just be careful, guys, as you are going through these examples with your homework. And, think about, like I said, if it helps writing out what the cards or, whatever the event space might look like, do that before you can come up with your answers. Okay, so this guy was number 16. Let's look at, number 24. So the instructions here are for 24. Use complements to find the probability that a card dealt from a full deck, again, no jokers, is as stated, and they're saying same thing, count the ace as a high card. So this time they want us to use the rule for complements to help us find the probability for event 24, which is below a queen. So below a queen, again, what cards are we looking at? Remember, the ace is a high card. So what cards would we consider below a queen? All right, Logan, 2, 3, 4, 5, 6, 7, 8, 9. You missed a 10 and the jack.
I always forget about the 10.
Oh, poor guy. All righty, very good. So 2, 3, 4, 5, 6, 7, 8, 9, 10, and jack. So you can see pretty much the only cards above a queen, guess I'm going to put that here, above the queen would be our king and ace, because they're asking us to use the ace as a high card. So this is kind of where this idea of rule of complements come into play. Because if we did it the way we did our probability for number 16, you would have to add the probability of 2 with the probability of 3 with the probability of 4, and so on and so forth. But because the cards above a queen are only 2 cards, we can actually start out by finding what the probability of these 2 cards will be, because it's only 2 events as opposed to, how many are these? 12 events, I think. You can use the rule of complements to find this answer. So that means find out the event or the probabilities for, king and ace, and then subtract that from 1, which will give you the probability of below a queen. So coming back to our example here, let's start out by finding probability of king. How do I want to write this? Do I want to write it as, well, actually, I just realized something. Since this was below a queen, which means we're not actually including the queen in here. So for the above, we should actually include the queen as part of our calculation, because otherwise that gets left behind. So it will be queen, king, and ace put together. Where's my pen? Okay, so this guy should actually be the probability of queen with the king with the ace, which is what we actually calculated, remember, in part 16A, I think that was. So this should be 4 out of 52 for each one of them. And then, of course, reduce those down. You can reduce it down now or, later, however you want to do it. But we already know this part of our calculation. So this represents for, everything that was not included in this category here from 2 to J. So now using the complement, we can calculate this as 1 minus the probability of these 3 events. Any questions right now? Wendy, are you still with us? There you are. So what will this come out to be, guys? So same thing, get your answers ready, and I'll have you share your answer in the chat with me. And try to give me your answer in the reduced fraction form. All right, guys, go ahead, send me your answer. Okay, let's see. Okay, Logan, Brandon, Roman, Nicholas, Idali, Riley. Yeah, very nice. So again, this one is just basic fractions in terms of, you have to find your common denominator. So since this guy, the first number is 1, so it would be just 1 out of 1. Multiply that by 13. So that ends up giving us 13 over 13 minus the 3 over 13. And that comes out to be 10 over 13. And if you use your calculator, then the calculator, if you ask it to give you a fraction format, should also give you the same answer. So you can see with the rule of complements, we just have to find the probability for all of the cards which were not included in this event, and then subtract that from 1, and that gave us our final answer over here. Go ahead.
There's actually a quicker way to do this since we're dividing by 4, when we're adding it all up, it's pretty much whatever the total is, like 2 through jack is 10. So if you want to skip all the division, it's just 10 out of 13 because we already know there's 13. Does that make sense?
Yeah, because you are looking at 10 total cards in this event, right?
Yeah, so you
Yeah.
can skip all that. I mean, it works in this situation, but
Yeah, and again, if that is something you are comfortable doing, definitely go ahead and do that. It's just, if it does not work in every situation, then you have, the formal process of doing it. But yeah, like you said, since we know each suit has 13 cards and it's going to be the same for each of those 4 suits, yeah, you can count it that way also, Brendan. It definitely works. All righty, very nice. So just another example to work with the rule of complements. Now let's take a look at another type of example here. Okay, so for this, we need a little of this background information. So we're looking at number 42 over here. But before we can get into that, let's look at the instructions. So they're saying to determine the effect of their salespeople have on purchases, a department polled 700 shoppers regarding whether or not they made a purchase and whether or not they were pleased with the service. Of those who made a purchase, 151 were happy with the service and 131 were not. Of those who made no purchase, 201 were happy with the service and 215 were not. So they're saying using probability rules when appropriate, find the probability of the event stated. So actually, I want to transfer this guy over to our notebook so we can look at, how we can come up with these probabilities. So we will be looking at number 42 here. Let's save this and transfer this information over. So they're telling us we have a total of 700 shoppers. They are telling us out of those who made a purchase. Okay. So those who made a purchase, 151 were happy, 133 were not. And those who did not make a purchase, they are telling us 201 were happy, 215 were not. Okay, so that was the basic information we have in that. And here's our number 42. So this question is asking, come on, buddy. Okay, it's not letting me do this. There we go. So they want to know a shopper who made no purchase and was unhappy with the service, what would that probability be? And a shopper who made no purchase or was unhappy with the service. So you will see they're talking about same thing, no purchase and was unhappy, but the difference is this one here again has an and, this one here has an or. So how would those probabilities look like, in terms of and or? So just let me ask you, where do you think we should start with a problem like this one? This is probably going to be a good example of thinking about a Venn diagram for this guy. So let's do that. We'll create our little universal box over here. And then we've got our two circles. What do you think each of the circles should represent?
Made purchase and no purchase.
Okay, so think about this. Let's say if this guy is for the purchase. Wouldn't everything outside of it already become not a purchase? Right?
So I guess happy and not. I don't.
Yeah, very good. So that should be the two categories. And they're kind of telling us that in that instruction, right at the top, because they're saying regarding these shoppers, the department wanted to know, whether or not they made a purchase and whether or not they were pleased with the service. It was about purchase and service, right? So those actually tell you those will be our two categories here. You know what? Let's actually write this guy as happy with the service. All right, so looking at the total information, we know everything inside the rectangle has to add up to the total number of shoppers. So that's going to be a total of 700 people. So now looking at the people who made the purchase, they're telling us 151 were happy, 133 were not. For those people who did not make a purchase, they're telling us 201 were happy, 215 were not. So just take a second over here, guys. Think about it and tell me where should we place. Let's start with 151. People who made a purchase and were happy with the service.
Go in the
Maybe
middle.
intersection.
Okay, Ethan, go first.
I said the middle circle.
Okay, and Logan?
I said the same thing.
Same thing. All right. Yeah, very nice, guys. Because this is your overlap, right? Because they made the purchase and they are happy. So these guys go right here in the overlapping area. So now where do we put that 133 guys? They made the purchase but were not happy. Roman?
In the purchase circle, but not in the intersection.
Yeah, very nice, because these people obviously did not like the service, but they made a purchase, they shopped something. Perfect. 201, where do you think that is going? The people who did not, you know what, let's do the 215 first. I think that might be an easier placement. The people who made no purchase and were not happy with the service. Made no purchase and were not happy.
That would be in the outside of, in the square.
Yeah, very nice, because obviously, if they are not happy, they cannot go into the happy circle. If they did not make a purchase, they cannot go into the purchase circle. So perfect. The 201 is actually going outside over here. And then the last number we had was the 201, which they are happy with the service, but they made no purchase. So where's that number going? Happy with the service, but made no purchase. Brendan?
Did you mean the 215 on the outside? Of not
Did
having,
I switch my numbers? I did, didn't I? Sorry.
yeah, it's like I thought 201 was going in inside.
Sorry. Yeah, I think I misread that. So 201, happy but no purchase.
Inside the happy with service.
Happy with service. All right. So does this add up to our 700? Do these four numbers add up to 700? Just verify that.
Yeah, they do. They do.
Yeah, so because we know it has to come out to be our total number of shoppers. So you can see, once you have your little Venn diagram, then we can go ahead and answer our questions from number 42. So a shopper made no purchase and was unhappy with the service. So who falls under that category? No purchase and was unhappy with the service. So this is
That would be the 215.
That would be the 215. Very good, because that's the person which does not fall into any of the circles. So this is actually the probability we're talking about. So what do we do to calculate this probability?
Divide the 215 by 700.
Yeah, same thing, guys. You always take your grand total for the denominator, right? So we have a total of 700 shoppers who were surveyed. So that's the number you are dividing by. And this one, I would say, use your calculator to reduce the fraction, or you can start by dividing by 5, because both numbers end in 5 and 0. So you know 5 will be a common number in both. So let's see. When you divide 215 by 5, you get 43. And then what's 700 divided by 5? 140. And I don't think we can go, thank you, Brendan. We cannot go any lower than that, because I want to say 43 is a prime number. So I think this is probably as far as we can go in reducing our fraction. So that's going to be our probability for how many shoppers made no purchase and were unhappy with the service. Now you basically had the same question for part B, but instead of and, they're using or. So how will that change our probability here? So the shopper made no purchase or was unhappy with the service. So we'll go back to our Venn diagram here. Unhappy with the service or made no purchase.
So would we add the happy with service, not the intersection 201 and the 215?
Yeah, because the intersection, the 151 is they were happy and they made a purchase, right? And this one, of course, is no purchase and unhappy. So yeah, the 133 were the people who made a purchase, but obviously they were unhappy with the service, so they get included in here. Then you've got the 201 who were happy, but they made no purchase, so they fall under the no purchase category, so they definitely get added in here. And then the last one, of course, is the 215, which is what you did in part A, so you include that also. So again, if you were to look at this in a more formulaic way, and I probably should have done this in a different order, you're basically adding the probability of people who made no purchase, which is the 133. You're adding the probability of people who were unhappy with the service. And then, of course, you are taking in the people who were, both unhappy and no purchase. So kind of what you did in part A. So what do you think this total will come out to be? And can we reduce that? Okay,
I thought the 133 was people who made a purchase but were unhappy. Oh, they were unhappy. Never mind. Had to say it out loud.
that's okay. All right, so I got an answer. I think I saw, yeah, Ethan and Adali, very nice, thank you. So that's 549. Same thing, divide by the 700. And like I said, I'm not sure if we can reduce this or not. And it doesn't look like, because my calculator is giving me the same answer of 549 over 700. Sometimes they also use tables, kind of like this example over here. So they will sometimes do it in table form, but of course we are familiar with Venn diagrams. So Venn diagrams can also help us out with these types of examples. In fact, I think one example that I have might be with the table, because I think I did try to include one of these tables in there. So yeah, let's take a look at this guy over here, number 62. This is talking about the result of CNN's 2012 presidential election poll. So this is what we have over here. They're dividing it by gender. So male and female voters, in 2012, of course, Obama and Romney were our candidates. And then how many people, I guess, didn't vote for either one of them. So let's go ahead and actually take a look at, based on this table, what is our 62 talking about? So number 62 is find the probability that a polled voter did not vote for Obama, and find the probability that the polled voter is female. Alrighty, so let's start with part A. This is a person who did not vote for Obama. So let's calculate that first over here. Probability that a person did not vote for Obama. So what do you think we need to do for this guy? Where do we go? Where would we try and get that total from? So do we do, I don't know. Look at the people who voted for everybody else but Obama? So kind of like a compliment? Yeah, because when they're saying what is the probability that a polled voter did not vote for Obama, then obviously, that means you cannot include all of these people here. Because, obviously they voted for him. So that means you are looking at everything else that's remaining. So what do you think this probability will come out to be? Alrighty, I've got Brendan's answer. So let's see. If you are using the rule of complements, you will do 1 minus the people who voted for Obama. So if you add the total for people who voted for Obama, 9 plus 1 is going to be 10. So that's going to be a total of 50% of people who voted for Obama. So you're doing 1 minus, and again, we'll do these as decimals. So you can see basically you had 50% of votes for Obama. And then if you were to add these guys together, that would also add up to 50%. And of course, since you have the other category in there, you can see Romney's votes were just at 48%. So Obama had, 50% voting, which puts him at a little bit of a higher value. So again, you can use the complements, or in this case, since you only had 4 numbers, you could have added all the remaining percentages and you could have come up with that answer that way also. All right, very nice. So this was for part A. Now let's take a look at part B over here, which I believe was the probability that a polled voter is female. So what is the probability that a polled voter is female? And what do you think this answer will come out to be? So just get your answer ready in the chat. It should take you maybe just a couple seconds to get that number. And again, leave it in a decimal form as your answer. All right, go ahead and send it in, guys. What is the probability that your polled voter are female? Okay, I see. I think Brandon, you were the first answer I saw. Yeah, Brandon, Cynthia, Logan. Hidali, looks like you only got 50%. Roman, Riley, you also had 50% or 0.5. Nicholas. So remember, since you're talking about female voters, of course, you are adding up these 3 numbers together. So that does come out to be 53%, which will be 0.53. And we do actually, and that's a study they have actually done in these elections, there is a higher percentage of female voters than male. I think even last year, I believe that percentage was true. And that's kind of one of the reasons you will see if you guys follow any of these election discussions, that female, candidates will, obviously kind of target or, try to get out to more female voters because they know that's a big part of their voting population. Okay, so we had talked about just, how you can use probability with the genetics, makeup of pretty much any living form. And we had seen an example of sickle cell anemia last time by using that Punnett square. So just based on that, we were again trying to see how we could use these probability rules to also help us out with these calculations. So they're saying use probability rules to find the probability that a child will have neither sickle cell anemia nor a sickle cell trait. And they're giving us part A if each parent has a sickle cell trait, if each, part B says one parent has sickle cell trait and the other has no sickle cell gene, and then the third one says one parent has sickle cell anemia and the second parent does not. So just different scenarios, and then based on each scenario, we need to calculate what the options will be. So the first thing we need to do is actually come up with what the Punnett square would look like, and I guess we have to make our own. So let's do that over here. Okay, so actually, we will need to create, I think, a different one for each one of these situations. So let's go back to this guy here. Alrighty, so this one is telling us for part A that each parent has sickle cell trait, which basically means they are a carrier, but don't have the disease, themselves. So remember, with our Punnett square, this would be no, and then a small s, because remember, it's a codominant gene, so it's not a, S is a small letter because it's not a dominant gene. So in this case, since they're saying each parent has a sickle cell trait, both of them are going to be NS and S. So see, the combination would be no gene, even a trait over here. This child here will have a trait. This one will have a trait. And then, of course, the last possibility is the child could have the disease itself if they end up with both the SS genes in there. So the question is, what is the probability that a child will have neither sickle cell anemia nor a sickle cell trait? So if they're asking us that the child has neither sickle cell anemia, which would be this category here, nor they have the sickle cell trait. So how are we going to calculate this probability over here, guys? The probability that the child has neither sickle cell anemia, neither sickle cell anemia would be this one here, nor sickle cell trait.
One out of four.
Yeah, 1 out of 4, right? Because we are saying they shouldn't have the disease and they shouldn't be a carrier either. So you can see the only category that satisfies is the 2NN, combination, because that is where the child is not a carrier or has the disease. So you can do it, again, kind of like we did Venn diagrams, use this little Punnett square to help you come up with the possibilities. Okay, so same thing. Let's do our Punnett square over here. And let's see, for part B, they said one parent has sickle cell trait. So one parent will, of course, be the NS combination, and the other parent has no sickle cell gene, which means they don't even have the S gene in them. And then, of course, this case means the second parent is NN. So let's see, when we combine the first two together, this would be NN. Second one would be NS, so this child would be, definitely a carrier. The third option would be same thing, NN, and then the fourth option would be NS. So basically, two outcomes where they have no carrier and two outcomes where they have a carrier. So in this case, same probability question. What is the probability that the child has neither sickle cell anemia nor sickle cell trait? So they do not have the disease and they're not a carrier either.
One out of two.
Because again, those would be the same thing, right? We are looking at the child which would not have the S gene at all, because, of course, this child is a carrier. And so 2 out of the 4 options satisfy our requirement. So that's 2 out of 4. And of course, as a reduced fraction, that's half. So with this parent combination, you basically have a probability that the child will have no disease at all, and half a probability that the child will have the trait, so they will be a carrier. All right, so the last combination they are giving us is one parent has the disease, so they're just not a carrier, they are actually, diagnosed with the disease, and then the other parent has no sickle cell gene. So can you tell me, for the parent who has sickle cell anemia, what their genetic breakdown will be?
Both S.
Very nice. Yeah. And that's something, be careful about as you're going through these examples. So that's actually the parent, because they have the disease. Remember, that means they have both SS genes in them. And then the other parent who has no sickle cell gene, of course, that is the parent with the two N's. So what will our 4 outcomes look like here with these two parents?
All 4 would look like NS.
Yeah, very nice. So in this case, no matter, which combination you look like, the child will be born as a carrier, right? Because one of the parents has the disease. So answering our question, what is the probability that the child will be born with neither sickle cell anemia or nor a sickle cell trait?
0.
Yeah, because they will not be sickle cell anemic because they won't have the disease, but they will definitely have the trait. So since they have the trait, this will be a probability of 0 out of 4. Because, of course, you can see none of our combinations were NN over here, because for them to not have the trait or the disease, obviously you can see it's got to be the NN genetic makeup. And obviously with this set of parents, that is not an option. So just again, to show you how the little probability rules can be applied in different ways, when you're looking at different types of examples. So any question on this example over here, guys? Okay, so we've looked at an example with the Venn diagram, an example with the table, and one example with the genetic breakdown. So again, guys, your homework for chapters 2 and 3 is due on Monday, the 4th. So when you come to class on Monday, we'll be taking our chapters 2 and 3 exam. So remember, you have a separate quiz for chapter 2 and a separate quiz for chapter 3. Please, use your time wisely to get all of those homeworks caught up on. And if you have any questions, let me know. I'm probably going to be working through the afternoon. So if you guys have any questions, definitely send me an email and I can help you out. And then those of you who want to stay back and ask me questions, please do that. And the rest of you, I will see you guys on Monday morning. So good luck, everyone. Have a wonderful weekend, and I will see you on Monday. Bye, guys. Take care. Bye.